Hi, hi everyone. Welcome to a new virtual tour of the European Southern Observatory, also known simply as ESO. My name is Farid Char, and with the producer Hector Salas, who will be your guides during this journey to ESO's La Silla Observatory. Um, from my side, I am one of the guides of Paraná Observatory for more than 10 years. um, I have more than 15 years of experience in astronomy outreach and education. I am part of an astronomy center in the University of Antofagasta, and one of my main hobbies is the astrophotography. Well, so as I told you already, I am not alone. I am with Hector. He will be the producer. Hello, Hector. How are you?
Hi, Farid. I'm happy to be here once again. So, I will introduce myself to everybody. My name is Hector Salas. I'm a PhD student at the Leibniz Institute for Astrophysics in Germany. I work mostly with topics related with the circumgalactic medium, that is the environment that surrounds galaxies. And I have been a member of the team of guides for Parallel Observatory since 2019. I started there while I was doing my master's in the University of Antofagasta. And as Farid mentioned, today I'm going to be the producer, and that means that I will be reading all your comments or questions and try to find the answer if neither Farid or I know them. And I will also be playing the videos and changing the pictures and whatnot. So we are.
Okay, thank you very much, Hector. So, well, yep. So ISO would like to join you during these virtual tours, taking astronomy directly to your home or wherever you are. So please remember that you can send your comments or questions to this streaming. I imagine you might have some questions already. So for this purpose, you can leave your comments or questions in the Facebook or YouTube comment box, and Hector will be collecting all your questions or greetings, and we are going to respond to those questions later during this virtual tour. Okay. Well, so and also please don't forget to share this experience if you enjoy it, and you can share this virtual tour using your buttons on Facebook or YouTube. Okay, so now we are going to start, and the first thing I'm going to do is explain a little bit about the organization, about ESO. So we are going to talk about what is ESO and what are the countries involved in ESO. So we are going to take a look at the picture right now. So we can see that ESO is an intergovernmental organization composed by 16 member states. Its headquarters are located in Germany, and Australia is also a strategic partner of ESO. So in this case, Chile is the host state, and it's the home of to all ESO observatories. Now, since the 60s, and with the purpose that I mentioned already, ESO choose one of of the best places on the planet for astronomical observations. In this case, the Atacama Desert in Chile. So at that time, Chile had started a site exploration campaign to attract international observatories such as ESO to our country. So Chile offered land, and ESO chose the area with the best conditions. So ESO's mission is basically to design, build, and operate astronomical observatories. And what for? To enable important scientific discoveries and foster cooperation in astronomy. Now, we are going to take a look at another picture to see the observing sites. So here you can see in this picture the three observing sites in Chile. So first we have the Paranal Observatory. This observatory is home to the Very Large Telescope, the VLT. This is currently the most advanced visible light telescope on the planet. In the future, the Paranal Observatory will also host the Extremely Large Telescope, or ELT, which will become the world's largest visible light telescope. And near there will be the CTA, an array of telescopes for the detection of gamma rays. Then we have Chajnantor, the site where the ALMA and APEX radio telescopes are located. ESO participates in these radio astronomical observatories with its international partners. And finally, we have La Silla Observatory, the site you will be visiting today. This was the first observatory built by ESO in Chile, 2,400 meters above sea level, in the region of Coquimbo. So we will go there virtually during the next hour. Okay, so let's travel to La Silla Observatory. We're going to show you an animation traveling over Europe first. Here we are. So looking at our planet, we start this journey by land in Europe, since I must mention that ESO is an organization composed by European members. So on this map, outlined in white, we can see the different ESO member states. And in this case, Chile is the host country and home to all ESO observatories. To see the sites, we will travel to the Chilean mountain range. And as we move over the Atlantic Ocean, let me tell you more about ESO's mission. To give you an idea, ESO tries to devise which type of instruments are needed to study the universe, and then designs the pieces, build and operate telescopes, responding to observational requests from around the world, and encouraging cooperation in astronomy. Okay, we are almost there, and we will see very soon a mountain range with a lot of domes. So you can notice that in the Atacama Desert, of course, it's very dry. It's the non-polar driest desert on the planet. And look at the shape. Now we are approaching La Silla. So look at the shape of this hill. Does it remind you of anything? Perhaps a horse saddle? Well, in fact, the mountain itself and the observatory later were named after a saddle for horse riding. So over the years, ESO's La Silla Observatory has become the perfect viewpoint to study the universe. So now we can see that La Silla has many telescopes of several sizes. So we can see the names of the telescopes as we are approaching to the mountaintop. We can see the different names like the MPG ESO 2.2 meter telescope, and we can see different ones like ESO 1 meter Schmidt, etc. So, well, just to finish my explanation about this, so La Silla was chosen by the astronomical community as an observational site at the beginning of the 60s. So La Silla enjoys a large number of clear nights per year, and still and dry atmosphere and dark skies, far away from artificial light sources. Okay, so this observatory was officially inaugurated by ESO in 1969, and some of the telescopes that we already saw in this animation are now out of service. So currently we have 10 telescopes in operations. Okay, and two of them are operated directly by ESO. So the other telescopes, several of them are robotic, and they belong to other institutions with ESO providing the facilities and the necessary support. Okay, we are going to show you the mountaintop in La Silla. So, Hector, can you please share the screen? Okay, thank you. So, this picture right now, this picture in your screen is La Silla Observatory, and you can see an overview of the mountaintop here. Okay, so we have, of course, a very nice landscape. We have all the telescopes there. In this picture, the sky is, well, we have almost sunset, as you can see. So we are going to begin this journey, this virtual tour, going inside of the largest telescope the 3.6 meter ESO telescope. Okay, so we are going to return to show you the first stop of this visit. This will be the ESO 3.6 meter telescope. This is the telescope just in front of you. Okay, so this telescope is very interesting because the main instrument inside is an exoplanet hunter. So I am going to talk more about this in a few moments. Okay. Well, we are going to go inside. Okay. So this is the ESO 3.6 meter telescope. Okay. So this telescope is also usually named the 360. This is the usual name by the staff at La Silla Observatory because the name refers to the diameter of the main mirror. So back in the mid 70s, it was one of the largest telescopes in the world. Currently, it hosts an exoplanet hunter. Its name is HARPS, a highly specialized instrument. And this instrument is used every night to search for other planets outside of our solar system. So, what do you notice about the dome from the inside? Well, it's huge, right? It's a very big dome. The altitude from the first floor to the dome is 25 meters. And all this structure of the telescope is equal to a seven-story building. So everything seems small here as compared with the telescope. So for example, can you see anyone over there? Maybe a person? Well, yeah, there is a person. And you can see this person right there. Okay. So I am going to do a close up and you can see that we have a person over there. So this person is just below the blue structure. So, well, this reference helps us to distinguish the telescope itself from the rest of the structure. So now we are going to explain this in more detail. So I am going to come back to the main view of this telescope, and I am going to explain the main uh, portions of this telescope. So I am going to open a picture, this one, and I am going to explain a little bit about the telescope. So you can see three things on this picture in the right side. So first, in dark blue here, we find the structure supporting the telescope itself, basically the mounting. The mounting works as a huge arm supporting the telescope and includes several systems that provide power, such as electricity. On this arm, parallel to the Earth rotation axis, the telescope moves to follow objects in the sky during the observation. Now, going upwards in lighter blue, in this color here, we have the telescope's body holding the 3.6 meter or 360 centimeters main mirror and the secondary mirror. Now, where is the main mirror? Well, the main mirror is not visible now because it's covered by its protection system, this black structure. Okay, so this is a system of tabs which open and close to protect the mirror from dust or moisture when the telescope is in this, well, let's say parking position. In the black tubular structure here in the upper part, we have the secondary mirror, which gathers light from the main mirror, and after that, it reflects this light to the instruments analyzing that light. So you will notice that the main mirror has a hole in the middle here. So the light is sent to the instruments through this hole. And where is the instrument? Well, the instrument in this case is HARPS, the exoplanet hunter, is not visible right now because it's completely isolated in another room on another floor of the building. So basically, HARPS, okay, is an exoplanet hunter because it's able to detect something very very special. This can detect small variations of um, of of how the star is being attracted by the gravity of a planet, and we call this a method of finding an exoplanet. Well, we are going to show you a short animation in a few moments. I don't know, Hector, if you have this. Okay, this one. Um, so look at this animation. Okay, so basically we have a planet there orbiting a star, and because the planet is massive, okay, of course, well, the planet of course is orbiting the star. Okay, can you put the animation? Thank you. So the planet, of course, is orbiting the star, right? Because the star has well, a lot of gravity, but the star is also being attracted by uh, by, by the gravitational field of the planet. Okay, so this is a very teeny, a small variation, and in the position of uh, the star, and but in this case you can see that uh, let's say the spectrum of the star is changing. Can you see? I mean, the absorption lines are moving to the left and the right, going to the blue and the red corner. So this behavior is an indicator, a strong indicator that there is a planet orbiting that star. Okay. Well, so basically, this method to discover an exoplanet is called radial velocity. Okay, so and this is why HARPS is so important in the discovery of new exoplanets. Okay, so just to finish the explanation here, um, the 360 began operations in 1977. And from the beginning, it represented a challenge for engineering and for ESO as an organization. European astronomy was basically gathering talents from several countries to build an optical telescope in the 4-meter category, the largest and most advanced category that existed at this time. And why was such a large telescope needed? Well, in astronomy, objects are analyzed through their light. The more light we collect, the more we can learn. In this case, a bigger mirror will capture more light and therefore more information will be available. We will be able to see fainter objects and smaller details. Okay? Now, how do you think this giant telescope moves? Well, we have a short video to show you how this telescope is moving. Okay, so this is basically how the telescope is moving. As you can see, it's a huge structure. Well, so a mirror for astronomy is not just any mirror, since its shape and surface must be perfect at the scale of fractions of thousands of millimeters. So to achieve this in the 1970s, an extremely thick mirror was manufactured with 53 centimeters thick on average. But this also implies an extremely heavy mirror, so the mirror weighs 11 tons. This is the equivalent of two African elephants. So if we want to build larger telescopes, we need to find other solutions. So how was the next step taken? We will see it later when we visit the NTT telescope. the New Technology Telescope. Okay, so we are going to go outside now. We are going to come back to the previous screen, and we are going to continue. But before moving to the next telescope, I don't know if we have some questions from the public, Hector.
Yes, we have many greetings. We have Gavin Dude that says Ciao ESO from San Marino. We have Sanjeev saying Namaste. We have Sway Graven, regular in this virtual tour, saying love from Amsterdam. We also have George, also a bit of a regular in these streamings, saying good morning from Mexico. Now we have a quick question to clarify whether the mirror or the whole dome is 3.6 meters, and the mirror is 3.6 meters in diameter. Do you know the actual sizes of the dome structure for it? I don't know that number.
You mean the dome of the 3.6?
Yeah,
Well, this is very big. I think it's more than 30 meters because this is bigger than La Silla. Um, okay, the diameter of the enclosure, first thing, is like 31 meters. Yeah, 31 meters. And the altitude of the dome is 441, if I remember, if I am
yeah. And you says
remembering correctly.
already that should be like
41
a
meters.
six-story building.
Excuse me?
That you already mentioned that it should be the size of a six-story building,
Yeah, it's a seven-story building actually.
seven-story.
Yeah, yeah,
Uh,
yeah. But yeah, as far as I
it's
remember,
big.
it's 41 meters height of the enclosure. Yeah,
Okay, and
yeah, it's
we also
definitely.
have a question here regarding the pictures that we have right now. Is this common to get clouds at this altitude here?
Well, in the Atacama Desert in general, we have a good average of clear nights. Now, this average of clear nights, it depends because, for example, near the Paranal Observatory in the Antofagasta region, yeah, you can say that you have more clear nights, about 320 or something like that. In La Silla, as far as I know, you have something like 280 clear nights per year. So that means that you can expect things like clouds, high humidity, maybe even snow sometimes. So, for example, in this picture, you can see some clouds. But let's say on average, in La Silla, you can expect something like 280 clear nights per year. So, yeah, of course, you will have some uh, nights that when you cannot observe. But in general, and if you compare this with with other places, other countries, other observatories, it's still a very good average. This observatory is located above 2,000 meters above sea level. So this is in general good altitude because usually the clouds are not going uh, too high. But in this picture, for example, yeah, you can see that you have some clouds. So let's say that on average is 280 clear nights. Usually in winter, you can expect bad weather and some problems to do observations.
Okay, thank you for your answers for it. We don't have any more questions so far, and I would like to invite our audience to send any doubts or comments that you might possibly have.
Okay, thank you, Hector. So we are going to continue. And yeah, as I told you already, we are going to visit the NTT, the New Technology Telescope. This telescope is located there. Now, so the NTT, as I told you already, is an acronym. It means New Technology Telescope because the NTT was a pioneer as it includes groundbreaking technology that currently is very important for modern telescopes. Okay, so If you compare the NTT with the 3.6-meter telescope, you can see some difference, right? I know this is from the distance, but you can see that the dome is different. It's a different shape, okay? So you will see that the difference in the dome and the dimension of the enclosure is very important, because you can see that uh, the mirror of the entity, as I'm going to explain later, is almost the same size of the mirror here. But you can see that this enclosure is much smaller, it's more compact. So basically, because of the new technology being applied here, the people was able to build an enclosure with a more compact size, and of course that equals to less money spent on this structure. But the mirror is more or less the same size of the mirror here. So this is an important advancement in the technology to build new telescopes. Okay. Okay. So we are going to proceed, going to this telescope, to the NTT, and here we are. So, do you remember uh, the structure of the 360, right? Well, its huge dome and how small the person seem inside. Well, in this case, the building is practically attached to the telescope, and if we stand in front of it, we will look approximately, well, I don't know, this size, more or less. Okay, so this is a totally different concept. Okay, so this enclosure is much smaller, and the way of how the telescope is moving is also totally different. Well, the NTT was inaugurated in 1989, okay? And it has a small and very compact octagonal dome with a system of flaps, okay? This represented in its days an evolutionary leap in the construction of telescopes, since it allowed hosting instruments in smaller and lighter structures with improved airflow on the inside. So basically, this was an improvement in the construction of new domes, and basically the previous dome from the 360 is is now considered some classical uh, dome structure. So let's say that mostly all modern observatories are uh, are hosted in smaller and more compact enclosures. Okay, okay. So basically, in this case, uh, we can see that the telescope mounting is also completely different. Here you can see the entire building spins around 360 degrees. Now you can see the main mirror here, okay, on this round structure. I am going to do a close up and you will see the mirror there. This is the mirror, okay? So this disc here is the mirror, and we can see that it's reflecting some light, okay? So do you remember the 53 centimeters thick mirror of the 360? Well, the NTT mirror has almost the same diameter as the 360. In this case, is 3.58 meters to be precise, but it's also thinner. This mirror is only 25 centimeters thick, yeah, and is also much lighter. In this case, 6 tons. This is like the equivalent to just one elephant. So, to keep the mirror, the perfect shape of this mirror as the telescope moves, there is a system of actuators or pistons below the mirror. So we can see that uh, there's a structure here, and underneath we have a system of actuators. I am going to show you the telescope from the opposite um, perspective. So basically, in the underneath, we have these actuators. We have 75 actuators going up and down to keep the perfect shape of the mirror. In this case, it's a concave shape. So this system is controlled by a computer, and we call this system active optics. Okay, this is the name of this technology. So active optics was developed by ESO and represented a significant technological improvement in the construction of the new generation of telescopes in the 10-meter category. Active optics has also been applied to all large modern telescopes, including the Very Large Telescope or VLT at Paranal Observatory, and it will be included in the upcoming Extremely Large Telescope or ELT, right now under construction near Paranal in the Armazones mountain. Now, where's the staff? Where's the staff of La Silla Observatory? Well, we have something like 30 people working in La Silla on different telescopes and doing different kinds of procedures. But they are not here. They are not in the telescope. They are located in another place. In this case, it's a specific control room. And in this control room, of La Silla Observatory, we have all the scientists working at night in a much more comfortable space. And the control room is located in another building quite far from here. And actually, we have a short video to show you how it looks the night operations at La Silla. So I don't know if we have. Okay, this is the animation, and you can see that we have basically two workstations. One of them is for the 3.6-meter telescope, and the other is for the NTT. So you can see that it's basically a lot of computers for different purposes, and we have some people working there, um, basically supervising the night operations. So as I told you already, this control room is not inside of the telescope; it's in another building. Is in the same mountain top of La Silla, but it's not inside of the telescope. So they are in another more comfortable location to supervise the night operations. Okay, um, so this is basically all the information regarding the entity. Hector, I don't know if we have some additional question. You are mute, Hector.
Oh, sorry for that. Yeah, we haven't got any more questions or comments, so I'm going to ask you one myself. What happened to this mirror? Do we need to do some sort of maintenance or clean them somehow?
Yeah. So basically, for the cleaning of this kind of mirrors, we usually have two ways to clean the mirror. One is an easy way and a more complex way. So the easy way to clean this kind of mirrors is by using an element called the carbon dioxide in the form of like, let's say, snow, or it's more like a foam. So this carbon dioxide is applied on the mirror, and this element is important because we can remove dust from the mirror. Okay, so usually, for example, in parallel observatory, we do the same thing. We have to rotate a little bit the mirror, and we apply this carbon dioxide, and basically this element will remove dust, and everything will fall to the ground. And this is the best way to keep the mirror free of dust. And this is a simple way to clean the mirror, and you can do that uh, usually once a month. But the other way to clean the mirrors, and the more complex way and the most effective way to do this general cleaning, is a process where you need to remove, extract the whole mirror, because you need to do a process called recoating. It's called recoating because the surface of the mirror is a very thin layer of aluminum. So into recoating, you need to remove the aluminum layer and you need to put a new one. So in this process, when the process is finished, the mirror looks like a new mirror. And this is interesting because this is the main reason of why you can still operate with the same mirrors from several decades ago, several decades old, and um, and the mirror will look like a new mirror. So all this process usually takes a few days, and when the mirror is ready, you can take the mirror and you can place the mirror again in the telescope, and the telescope can restart operations as a new mirror, let's say. So this is basically how we can clean the mirrors, and that's why we can keep using the same original mirrors from several the same mirror uh, that is decades old.
Okay, thank you for it. And how about another question? We have showed them a lot of things about the observatory through this virtual tour, but can people go in person to the observatory?
Yeah, yeah, of course. Do we have uh, a system of public visits to La Silla and Paranal Observatory. So basically, the people can go there for free, um, but there is a process to do that. You need to do an online booking, and after that, you have to go in your own transportation to get there. Now, La Silla is located a little bit far away from the closest big city. In this case, La Serena is something like 2 hours and a half. So you need to take your time to get there, and and basically the visits there is all Saturdays. Um, the time of the tour is at 10 a.m. Uh, it's more or less 3 hours of the tour. Now, the important thing is that there is a little change in the timing of the tours because from September to March, the start of the tour is from at 2 p.m. Okay, and there is also another slot on Sundays, April to August. You have another tour starting at 2 p.m. Okay, so basically, all to summarize, during all the year, you have tours on Saturdays, starting at 10 a.m. September to March, Saturdays from 2 p.m. and also Sundays, April to August, starting 2 p.m. But in all cases, you need to do an online booking, and you need to do that with some time in advance in order to secure your spot. And you need to take your time because this is a little bit more far away from the closest big city, in this case, La Serena.
All right, thank you for it. And also to remind that we can also have in-person tours to Paranal Observatory as well.
Yeah, of course, we have tours in person to Paranal every Saturday, 10 a.m. and 2 p.m. So, yeah, in this case, well, Paranal is 120 kilometers away from Antofagasta. It's only 1 hour and a half. And same system, you need to do an online booking. You need to go with your own transportation system. Uh, but it's of course very nice because you have the opportunity to visit in person this big facility, and in all cases, Paranal and La Silla, you will have tour guides in charge to show you the main facilities, and of course, it's very impressive.
Yeah, and just to clarify, the online booking is at www.iso.cl, I think.
Yeah, in ESO.cl, and you have to just look for the proper section. In this case, public visits to the observatories, and you can find more information about that.
Okay, we have a couple of questions right now. So one from Michael, a bit technical question. How long does it take to realign or recalibrate the mirror after the recoding process?
Uh, okay, well, usually when you finish doing the recoding, if that's the question there, it's usually 2 or 3 days or something like that. But usually, well, you don't need a lot of time to do that. Maybe a few hours after you put the mirror in its place again. But that's why all the daytime operations in an observatory, in this case La Silla, or it could be Paranal, etc. Well, the daytime operations is usually for engineers, for people in charge to prepare the telescope for the next observation night. So usually once you put the telescope, the mirror in its place after a recoding, probably you need only a few hours to give everything ready to restart operations.
Okay, thank you. And we have a question here. What is the farthest galaxy found by La Silla Observatory? Do you know for it?
The what? The third? Oh, uh, well, I'm not quite sure, but anyway, this is the kind of question that will never have a definitive answer because this can change at any time. For example, well, if I remember correctly, it's uh,
Okay, so
let me think. It's
I'm
maybe
looking
it's
at a press release from ESO
mm,
from, let me see what it is. This is very old, from
probably from
1990.
the 19, right?
Yeah, from the 90s, and
Yeah.
it's showing a galaxy that is at redshift. Let me get the actual number. 11, which, if we translate that to light years, is at about 10,000 million light years away. And that was in the
Okay.
90s. So with other newer observatories or with Paranal, we probably have gone way more farther than that.
Yeah,
And
yeah,
also,
I think so. So usually when you have a larger mirror, with more modern equipment, you are able to discover more distant or fainter things. So La Silla is pretty old right now, and of course you have a lot of different milestones from La Silla, but probably at this time other observatories have been able to achieve this kind of milestone and to discover even far uh, more far away these galaxies. Anyway, I think that the most important discoveries from La Silla in the current time is more related to exoplanets because of this highly specialized instrument, the HARPS. And actually, in a few moments, Hector will show you a short video summarizing the main milestones from all ESO sites. I mean, from La Silla, Paranal, and Chajnantor. So basically, you will have a quick look at the top 10 discoveries from all ESO sites. So basically, you can have a better idea of the main scientific discoveries or milestones from La Silla. Okay, so Hector, maybe we can show this video now.
yeah, give me a second and I will put them on the screen.
Thank you.
So,
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam, or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, very good. We have one last important milestone. Maybe you can show you, Hector, please. Just to
One, yeah, this
yeah,
one.
I think this one. Okay, in this case, this short animation is related to another important milestone. This is about the discovery, the first, um, uh, let's say, discovery of an black hole. And in this case, this was possible with an important uh, collaboration from the Event Horizon Telescope. The Event Horizon Telescope is a collaboration between different radio telescopes located on Earth. And basically, this image here was the black hole in the center of Messier 87, a massive galaxy in the close galaxy cluster in the Virgo constellation. It was located 55 millions of light years from the Earth, and with a mass of 6,500 million times the mass of our Sun. Okay, so we are going to finish this experience with a quick visit to the night sky from La Silla Observatory. So in this picture, you can see a lot of stars, of course. You can see a lot of constellations. And basically, I will show you very quickly some of the most important ones. So you can see here the entity, and here you can see very famous constellation. This is Orion. So this is in the mythology, a hunter, and you can recognize this constellation because you have these somewhat aligned stars here. So these stars are in Chile are commonly named Three Marys or Tres Marias in Spanish, and they are very popular in the night sky. Another important object near here is this. This is called the Orion's Nebula. So basically, you can see this object even with your naked eye, because it's very bright, and that's why basically Orion is a popular constellation from both hemispheres, the northern and southern hemisphere. Okay, so this is a constellation that we can see here, almost in the horizon. Okay, now if we continue going up, you can see here the brightest star of the sky. This is Sirius. Sirius is the brightest star in the sky, and we can see that Sirius belongs to a constellation called Canis Major. Canis Major is one of the hunting dogs of Orion. Orion has two hunting dogs. This is one of them. So basically, the brightest star in the sky belongs to a constellation that is connected in the mythology to Orion. Okay. Now, in this picture, you can also see a lot of stars here, a more higher density of stars here, because you are looking here at one of the Milky Way arms. So you can see that this area has a lot of concentration of stars and nebulas if you compare with this area of the sky or this area of the sky. So the Milky Way is our galaxy, of course, and the solar system is only one of the systems in this huge structure. So basically, from our planet in a dark environment like this one, the Milky Way looks like this. Okay, you can see one of the Milky Way arms here. Now, if we turn the view a little bit, you can see something interesting. You can see a couple of spots here. Those spots are the Magellanic Clouds. So basically, this one is the Large Magellanic Cloud, and this one is the Small Magellanic Cloud. They are basically galaxies. They are not clouds, but we call them Magellanic Clouds because the first one to record them was Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So at this time, no one was aware of what a galaxy is. So that's why we call them the Magellanic Clouds. Now, the Magellanic Clouds are irregular galaxies and they are orbiting the Milky Way. So that's why they are interesting. And they are only visible from the southern hemisphere. Okay? So this is important also to mention. And the last important thing here, we have a very popular constellation. This is the smallest one. This is the Southern Cross, this one. This is the smallest constellation in the sky. And you can see that, well, it's not perfectly right. It's a little bit tilted. But there's something interesting about the Southern Cross. The Southern Cross is a very good guide to find the South Celestial Pole, or basically the South Pole projected in the sky, the geographical South Pole projected in the sky. So in order to find that area in the sky, we have to basically project 4 times and a half the longer stick, this one. So basically, I am going to do that. I am going to project 1, 2, 3, 4.5, and more or less like here, we have this South Celestial Pole. And basically, if you basically look at the horizon, if you try to have a perpendicular line and you look at the horizon here, you are basically looking at the south cardinal point. So it's interesting to know that because it's a good way to find the south. Okay, and just to finish, we are going to show you some of the telescopes again from La Silla Observatory. We have the telescopes from this perspective, you see, and I am going to finish this virtual tour going toward the residence of La Silla, because the residence is the place where the staff is resting at night. You can see all the telescopes here, and you can see that the residence is located basically in the other end of the observatory. So we are going to stop here to show you that this is basically a nice place to rest. This is the photographer who took all the pictures we show you in this virtual experience. And in this view, we can see the center of the Milky Way. So basically, from any place in La Silla Observatory, you can see a fantastic night sky, and this is basically the center of our galaxy. So this is the important information I have to tell you from this point. Okay, Hector, I don't know if we have one last question.
Yeah, we have one last question from Marcin. He asked us to talk a bit about the adaptive optics.
Yeah, well, adaptive optics is a system that it was applied in Paranal Observatory, and it's basically something different because for adaptive optics, you need to include a deformable mirror. So a deformable mirror is basically another mirror in the system. I mean, you have the primary, secondary, tertiary mirror, etc. But you have in all the system a tertiary mirror able to, let's say, compensate the atmospheric turbulence, because the atmosphere is a mass of gases, the gases is moving, so at some point, what you will see that the stars will look distorted, and our solution to correct that problem, that distortion, is to include a deformable mirror able to compensate those distortions. So basically, in the final reflection of the light, the star will look like more clear. Okay, so if you look on the ISO website, you can find us a few comparisons of star or cluster, etc., without adaptive optics applied and with adaptive optics applied, and the difference is very clear. So adaptive optics is another important system being applied in modern telescopes, modern observatories, to compensate, in this case, the effects of the atmospheric turbulence. So the final result is more or less like emulating the conditions of the outer space.
Yeah, and just to complement your answer a little bit, when we use the adaptive optics, we either observe a known star that we know how to look in the images correctly. So that's where we can calculate how to compensate the atmospheric disruptions, or we use a laser to create a virtual star by ionizing a layer of what was- I don't remember the element right now. I think it was iron.
What?
The layer that we used for the laser was from which element? I cannot remember it. I think it
I
was,
mean the sodium atoms in the high
yeah,
atmosphere.
sodium. It was sodium. I could not remember that it was sodium. So the sodium atoms in the atmosphere, upper atmosphere, gets excited and then they emit light. And since we know how this should look on the images, we can calculate how to compensate by deforming this mirror. And finally, just to finish, George is asking us if we could use these adapted active optics or adaptive to reduce the impact of light pollution. And not really, in my opinion. There's completely different
Um,
effect.
no, I mean the active optic is something different. Is just a way to keep the concave shape of the mirror and to prevent or correct distortions in the concave shape. Uh, so basically, we are trying to preserve the same quality regarding the shape of the mirror, but the light pollution is a problem for astronomy in general. So the only way to reduce the impact of the light pollution is to reduce the light pollution. Uh, and that's why it's important to try to control, to minimize this problem, and to create some kind of rules to prevent this kind of contamination
Yeah.
from factories and new urban lights. Yeah.
Yeah, and just to clarify, this is not necessarily to have less light, but have light that is more efficient and is pointing towards the ground and not towards the sky. And I think we
Yeah.
are already past the time, so I say goodbye. Please share this with everybody that you know that might like it, and we will see you in a different time. We have tours every Saturday, La Silla and Paranal, Spanish and English.
Yeah, sure. So please uh, stay in tune with the ESO website and ESO social networks to know when will be the next virtual tool, Paranal or La Silla, English or Spanish. So, well, I hope you enjoyed this tour. On behalf of ESO, I want to say goodbye to everyone, and thank you so much for stay with us in this virtual experience. Okay, so thank you very much and goodbye.
Okay.